Welcome to Gradient Daily. Today, we're diving deep into a paper that is really shaking things up in the world of 3D content creation. We're going to be looking at a model called Trellis, which can whip up these incredibly complex 3D objects from just a few words. Seriously. So, let's get right into it.
Just look at the detail on this thing. You can see the wood grain, the different types of metal on the tools. The complexity is just incredible. Now, what if I told you that this entire 3D asset was generated from a single sentence? I'm not kidding. The ability to go from a simple text prompt to an object this intricate has been, a massive challenge in AI for a long time. But a new model from Microsoft Research, well, they might have just cracked the code.
So, the paper we're digging into today is officially titled, and it's a mouthful, Structured 3D Latents for Scalable and Versatile 3D Generation. But the model they introduce is called Trellis, and it comes to us from the folks at Microsoft Research. What this work does is it tackles one of the biggest hurdles in creative AI right now. How do you make high-quality 3D content just as easy to create as, say, an image from Midjourney? And you can imagine the implications here are huge for, well, everything. Video games, movies, architecture, you name it.
All right, so here's the game plan for today. We'll kick things off with the big challenge in 3D generation. Then we'll get into the secret sauce of Trellis, this thing called a SLAT, and its really clever two-stage architecture. We'll also touch on the massive data set they used, see the amazing results, and wrap up with a little critique on what this all means going forward.
So what is the big problem we're even talking about here? Well, you've seen how amazing text-to-image models have gotten, right? Text-to-3D, though, it's been lagging way behind. It's just a fundamentally harder problem. Creating 3D assets that are high quality, diverse, scalable, and, this is the big one, editable, has been a huge roadblock. Most models out there, they kind of struggle. They either can't handle complex shapes, the textures look off, or they spit out something that a professional artist just can't use. Trellis was designed to take on all of these issues head-on.
Okay, so let's get to the core innovation, the real secret sauce that makes Trellis tick. It all comes down to a brand new way of representing 3D objects inside the model's, well, mind, for lack of a better word. This is truly the cornerstone of the entire paper, and it's called the Structured LATent, or just SLAT for short.
So what exactly is a SLAT? Honestly, the best way to think about it is like a universal digital blueprint. You know how in construction you've got one blueprint and the carpenter, the electrician, the plumber, they can all use that same blueprint to do their specific job? Well, the SLAT is just like that. It's a single, unified, structured latent code. And that word unified is everything. Because from this one single blueprint, the model can then build the object out into a bunch of different 3D formats depending on whatever you need. And this right here shows you the power of that idea perfectly. Just look at any of these pairs. You've got the castle, the robot, the toolbox. The one on the left is represented using 3D Gaussians. That's great for super realistic rendering. The one on the right is your classic polygon mesh, the kind of thing you drop right into a game engine. Now here's the mind-blowing part. Both versions, the Gaussian one and the mesh one, came from the exact same SLAT blueprint. This is an absolute game changer. It means a creator isn't stuck with one file type. They can generate the object once and then decide later what format they need. It's just incredibly versatile.
Okay, so we've got the what. That's the SLAT representation. Now let's get into the how. How does Trellis actually create this powerful blueprint? Well, the answer is a really clever, really elegant two-stage architecture. And this isn't just one monolithic model. Think of it more like a finely tuned assembly line.
So if you look at it from a high level, the whole process is broken down into two main stages. The best way to think about it is coarse to fine. In stage one, the model basically creates a sparse voxel structure. You can picture this like a rough, blocky sculpture made out of Legos. It gets the overall shape and size right, but there's zero detail. Then, in stage two, it goes back to that blocky sculpture and populates it with all the detailed slats, filling in all the complex geometry and textures. It's like going from a rough sketch to a finished painting.
Now, before we pull up the full intimidating architecture diagram, there's one more key concept we need to grasp. It's the engine that drives this whole thing. Trellis uses a technique called Rectified flow. Now, I'm sure most of you are familiar with diffusion models, right? They start with pure noise and then slowly, step by step, clean it up into a final image or object. Well, Rectified flow is kind of like a supercharged version of that. Instead of taking a long, winding road to get from noise to the final result, it learns the most efficient straight-line path. The analogy they use is perfect. Diffusion is a winding country road. Rectified flow is a direct, straight highway. And because it's a straight line, it takes way fewer steps, which makes the whole thing a lot faster and more efficient.
Okay, here it is, the full two-stage architecture. And yeah, I know, at first glance it looks pretty complicated. But don't worry, it's all built around those key ideas we just talked about. 2 stages, both powered by rectified flow. Let's break it down piece by piece.
So let's zoom in on the first part of this pipeline, stage 1. This is where a component called the sparse flow transformer does its work. It takes your prompt, could be text, could be an image, and its only job is to figure out a rough outline of the object. It creates what's called a sparse grid of active voxels. You can just think of a voxel as a 3D pixel. So at this point, it's not creating the final detailed object. It's just deciding, okay, this part of 3D space will be the object, and this part will be empty air. It's basically building the foundational scaffolding.
All right, on to stage 2. Once that scaffolding is in place, the SLAT flow transformer takes over, and its job is to go to every single one of those active voxels from stage 1 and give it a detailed latent code, which is our SLAT blueprint we talked about. This is where all the magic happens. All the rich detail, the fine-grained geometry, the surface textures, it all gets filled in here. So if stage 1 builds the skeleton, stage 2 is what adds the muscle and the skin. And this whole two-step process is so important because it lets the model be really efficient. It focuses on the big picture first, and then it worries about all the tiny details.
Now, as you can probably guess, a model this powerful doesn't just happen. You can't train it on a handful of examples. A huge key to Trellis' success is the sheer scale and quality of the data it learned from. The researchers put together a massive data set of over 500,000 3D objects to get this thing trained up.
And here's a look at what that dataset, which they call Trellis 500K, is actually made of. They were really smart about this. They didn't just grab one big dataset. They strategically combined several. So they used the huge Objaverse XL dataset to get a massive amount of variety. But then they mixed in smaller, higher quality artist-curated sets like ABL and 3D Future, which have really great examples of specific things, like furniture. And then they filtered all of it to make sure the aesthetic quality was high. So what you end up with is a dataset that has both enormous scale and high quality. And that combination is absolutely critical.
Okay, so we've covered all the theory, the SLAT blueprint, the two-stage architecture, the giant dataset. Now for the really fun part. Let's actually see what this thing can do. This is where the rubber meets the road, where we look at the results and some of the really unique features that make Trellis stand out.
First up, let's talk hard numbers. This table puts Trellis head-to-head with other top models like Shape-E and Instant Mesh. Now, we're just going to look at 2 key metrics here. First is clip score, which basically tells you how well the 3D model matches the text prompt. For that one, higher is better. The other is FXD, which measures how real the generated objects look compared to a set of actual 3D assets. For that one, lower is better. And as you can plainly see, both the large and extra-large versions of Trellis are getting higher clip scores and lower FXD scores. In plain English, that means the results are more accurate and just plain look better than the competition.
And honestly, the numbers are one thing, but the visuals, they really speak for themselves. I mean, just look at the range here. You've got the super intricate architecture of this Victorian mansion, then you have the really subtle wood texture on this rocking chair, and then there's this sci-fi weapon with the complex metallic look. This is so far beyond just generating vague, blobby shapes. We're talking about detailed, diverse, high-quality assets from nothing but text.
And it's not just text, it works with images too. Every pair you see on this slide started with just a single 2D image as the prompt. And check out how well it captures not just the basic shape, but the whole artistic style. You see it with this stylized character and with the specific design of this biplane. Imagine you're an artist and you have a cool piece of concept art. This is a crazy powerful way to instantly start bringing that vision to life in 3D.
Okay, now this might be the killer feature. It's called local editing. And because that SLAT blueprint is organized spatially, you can actually change one part of an object without destroying the rest of it. Just look at this example. They generated a building, then they selected only the roof and gave it a new text prompt, A-frame roof. And look what it did. The model intelligently rebuilt just the roof into an A-frame and fit it perfectly onto the rest of the building. This is a massive, massive step towards making these AI tools actually practical for professionals to use in their daily workflow.
All right, but no model is perfect, right? And good research always owns up to its limitations and shows us what's next. So let's shift gears a little and take a more critical look at Trellis, both its strengths and its weaknesses, and think about what this really means for the future of 3D generation. So the strengths are pretty obvious. You get super high-quality assets, you can export them in different formats, the architecture can scale up, and you have that incredible local editing. But the authors are also really honest about the limitations.
One of the big ones is that it doesn't really understand material properties in the way a 3D artist would. It doesn't generate what are called PBR maps, things that tell a game engine how rough a surface is or how metallic it is. So if you're an artist who needs to put this asset into a scene with realistic dynamic lighting, that's a problem. Getting the model to predict those PBR materials is probably the biggest next step to make this truly ready for prime time.
Okay, so after all of that, what are the 3 big things you should remember? First, that SLAT representation. It's a new kind of digital blueprint that makes 3D generation way more versatile. Second, the 2-stage generation process. This course-defined approach is what lets it create such detailed objects so efficiently. And third, scale is king. This paper is yet another piece of proof that training on a huge, high-quality dataset is absolutely essential for getting these kinds of amazing results.
And that's our deep dive on Trellis. It's a really significant step forward for AI-powered 3D generation. If you enjoyed this breakdown, hey, do us a favor and subscribe to Gradient Daily. We do a new paper presentation every single day. We'll see you tomorrow.